Welcome to a new video of the data visualization class. In this lecture, we will go over how to use trees to understand data. Okay, so trees are very flexible and they allow us to model or to visualize hierarchical representations. They are very efficient and they have high interpretability. Sometimes it's easier to understand a tree compared to just looking at a regression model, like a linear regression model or any other type of models. As I will show you, there are different applications of trees. There are different type of trees depending on the things that you need to do. So here we have some examples on where you can use trees. In machine learning, in predictive modeling, when you want to show a classification problem or a regression model, it is possible to use a regression tree or classification tree to see which are the most important variables to predict the outcome in those models. We can also use, in the same context of classification and regression, we can use the trees during the exploration, during the EDA. Okay, another examples are when you want to represent a hierarchy, and there are some like, let's say that you have big like a category and there are subcategories, and you want to show the distribution or the share of these categories in the total. So there are some tree maps, that's what they're called, where you see some rectangles or even some circles, and they will show you how is the distribution of the different categories and subcategories. We also have some trees that are used to show how close or how far are some observations in our data sets. So we can use them in taxonomies and even for clustering analysis. We can see the distance between our observations using a tree, which is called the dendrogram. And we will cover some examples of these applications in this video. Okay, so let's talk about the first one, space filling trees. So the space filling trees is just to represent hierarchical data, and we have like a big rectangle, which is like the 100% of the data, and then there's another some like nested rectangles, and they represent like the different levels for one variable. So in this specific example, we have regions, so we have the sales per region. So the big rectangle is total sales, and then we have 4 regions, and you can see the contribution of each region to the total sales. Now, tree maps are even more useful when you have more variables, more categorical variables. For example, you have category and subcategory. So let's say that in the same example, we have regions, but also we have like families of products. So then we can have some nested rectangles inside each region. So that's when the tree map it starts getting very useful. In addition to the tree maps, we also have hierarchical trees. These are used to show how close or how far are some observations. So they can be used in taxonomy and also in clustering, as I mentioned earlier in the video. We will see an example where we see each observation, like which are the observations that are closer to that one. So you can kind of like identify groups. And then, of course, once you create a group, you can just do the cluster profile. So we use dendrograms for this purpose to represent these hierarchical trees. And we will also cover some examples about classification trees and regression trees. Okay, so let's go to our Colab. Let's cover our notebook. For this notebook, you will need to upload the 2 files, the Boston CSV and US Crime CSV. Both are available on Brightspace. And also here in the video, below the video in the description, I'm going to upload the files. All right, so let's check 3 different trees. So the first one is the tree maps. So the typical example here, we have data, and there are maybe this is like a store, and they sell, they have like 5 categories of products, like appliances, hardware and tools, construction, paint and decor, and outdoor. And we also have the sales. It can be millions. Okay, so to visualize it or to create a tree map, here I'm using Plotly Express, PX. And in the tree map, we use the information data. And also in the path is where you define which variables are going to be used to split the, like the whole space. So we're using here the category, right? This categorical variable. And then the values that are going to define the size of each rectangle, in this case will be the cells, or as we call it here, the values. So with these two parameters, you can create right away your first tree map. So this is how it's going to look. So we get the distribution of the different categories. So we know from looking at the plot that appliances right now, it's like the biggest contribution, the biggest contributor to the total sales, and outdoor is the category with the lowest number of sales. You can, if there are more variables, you will be able to click inside each category and see how the subcategories or the other variables are distributed. But in this case, we don't have more categorical variables. But let's check another 2 examples where we can do that. So remember this data set, we have used it before, tips. So it's a data set where we analyze the tip that was given by a customer. So we know some variables such as the day, the time where it was dinner or lunch, and even the gender of the person. Okay, so let's create the tree map, but please notice that here we have 3 variables. We have day, time, and sex. 3 variables. This thing that you see here, I'm gonna remove it and then I'm gonna explain it to you. What is that? The all. But let me remove it for now so you don't get confused. Okay. So we create our tree map. It's important to mention that the order matters here in the path. So if we're saying here day, then time, then sex, then we get at the upper level, we get the day, right? That's why you see Saturday, Sunday, and Thursday. But if you can change the order and the and then update the plot. It's gonna change how it works. Okay, so now you can see the values of total bill per day, per time, and also per gender. So if you click, let's say Saturdays, now you get the detail, like for each variable, for the time, dinner, and lunch, and for the gender. So it's very interesting, and it makes more sense when you have a multiple categorical variables. And remember that I removed something here. So this is just a trick to add a label here to the rectangle, to a big rectangle. You see the gray rectangle. Right now, that's like the complete space. So let's say that I wanna add a label here to say that this is like all data. So that's why we're adding like a constant, like from Plotly. I'm adding a constant, and this is the name of the constant. This is the constant value. So I'm just saying all. That means all data, and it will add the all here. But again, that's just a label. So when I'm inside the categories, for example, here I'm inside the time, so you can go back to the day, and here you can go back to all, to the original plot. But that's it. Again, this is not required. It's just something that you will see in Plotly Express documentation in their examples. They have this label. I mean, they change it sometimes, like in this example. The third one. Here, we're going to use the Gapminder dataset. Actually, we have used this dataset many times in our course. It has information about life expectancy, GDPs for different countries, different years. Okay, so let's create the tree map. But here, we're going to analyze the population per country, per continent. So please notice that here the constant instead of all is fine too, but we call it world to say like the whole world. And now we visualize the plot. So we see the continents, which is no surprise that Asia is like the biggest one, like the biggest contributor to the population. And you can see the different countries, right, inside each continent. Let's say you want to analyze better Europe or some specific countries, then you can explore that. So this is a really useful tool when you are in the EDA, or if you have a dashboard and you're analyzing results. So the three maps for sure are really helpful here, especially if you have two or more categorical variables. I think it's when you really appreciate the value of these two. All right, so we have covered the tree maps. Now let's talk about the hierarchical trees. So in the hierarchical trees, I'm going to use the dendrogram for clustering. So in the cluster analysis, the most common algorithms are k-means, right? That's the most popular one for sure. But also the hierarchical clustering is another popular algorithm. So in this data set, US crime, what we have is each observation is one state in the US, and we have some variables. The columns are variables with metrics about crime. So there is one metric that has the rate, like the number of murders per 100,000 of inhabitants. There are other like variables such as assault. Okay, so when you want to do the clustering, the first step, and this is similar to what we have done in our previous session with the dimensionality reduction algorithms, we need to standardize our data because even the rates, they have different mean values, especially because crimes are not the same. So, for example, in the case of murder, most likely the murder column, the mean value is going to be lower compared to assault, which is it's like a little bit more, the numbers are higher. So the mean value is going to be different. Therefore, these algorithms are sensitive to the distance. Then you need to standardize your data. That's why we scale it here, we transform it. We have done that in the past. So it's like finding the z values, right? To get everything with a mean equal to zero. Like, but by everything, I mean the mean value for each variable and the standard deviation and variance equal to 1. So once we have standardized our data, we apply the hierarchical clustering and we plot our dendrogram. So it's important to mention that this video is not about clustering, but I want to show you the idea of the dendrogram and how useful it can be even in other applications. Okay, so in the x-axis, this number 017, that's just the row ID. It's just the number of the row in your data set. So 0 means like the first position, 17 is like position 18, that's it. So this is like the states, pretty much. So one of these numbers is New York, another is California, and that's the idea. You can check your data set if you want, and you will see which number is each state. All right, so what is the interpretation here? And the y-axis is distance. It measures the distance. So, for example, when you see here 0 and 17 are connected, that means that they are close to each other. Same thing with state number 12 in the position 12 and the state in the position 31. They are close to each other. That when I'm saying that they are close, is not that geographically they are close to each other. No, it means that by analyzing their variables, the crime variables, they are similar. They are similar, right? In the context of our data set, they are similar observations. So that means that when you are going to create groups or clusters, those observations that are close to each other most likely will be included in the same, or they should be for sure be included in the same cluster or in the same group because they have similar values. At the same time, you can see here which observation or which states are very different from the crime perspective. For example, the state 43 and the state 0 in those positions, like the first one here and the last one, they are connected at a very high level, like like from using these blue lines. That means that the distance between them is high, or they are very different. That's the interpretation. They are very different. So this hierarchical clustering or this tree, the dendrogram, is very useful to identify observations that are similar, right? And observations that are very different. And that's the foundation in how to create clusters or how to create groups. So this is very useful. You can use this idea or this type of plots even during the EDA, just to understand like observations that are very, like similar and some that are different, and understand why they are the same or why they are like very different. A limitation of the dendrogram is like if you have too many observations, because here we have few observations. I think that I see 45, 46, so that means, oh, we have 49, so 50. Then it's a normal number. But if you have like 1,000 observations, then this dendrogram is going to be like too crowded. It's going to be difficult to read. Yeah, the value is going to decrease. Okay, so far we have covered the tree maps and dendrograms. And now let's talk about the decision trees, to be more specific, the regression tree first and then classification trees. So for that purpose, I'm going to use the Boston file, the Boston dataset. It was initially a part of scikit-learn, but then it was removed a couple of years ago. I don't think, I haven't checked if it's still available on scikit-learn, but the dataset is just about, or is used to predict median value of houses. So the y variable is the last column here, the median value of the houses. This is an old data set. It's like from the 70s. That's why the value is low. It's 24. It's $24,000, which is not. It's of course not a value that we see nowadays. And the variables here, just to give you an idea of some of the variables, we have like the crime. NOx refers to the pollution or like the particles in the air. We have the age, how old is the house. RM, it's an important variable, is then like the number, the average number of rooms per house. You see 6.5, you see decimals. It's because each observation here is not a house. It's like an area. And in the area, there might be like several houses. So this is the average in that area. So again, this is not for individual houses. Okay, and other relevant variables are LSTAT. LSTAT is like the lower status, or it's a measure of poverty. So it kind of like gives you an idea of the percentage of poverty in that specific region or area. All right, so we want to predict the median value. So we created three. I'm going to get into these details, but remember that you need to perform some sort of cross-validation if you want to create a predictive model. The idea is to evaluate your data in a test set in unseen data. So that's why you split your data set. Just for your reference, you should give it a look to K4 cross-validation. Okay, so we create a decision tree regressor here. This is where we train and create the model. Now that it exists, we can plot the regression tree. And this is how it looks, our regression tree. So it can be used to make predictions. Now, why this tree is relevant, and how can I use this tree? So it can be used to understand your data, to get insights. So typically, I highly advise my students to use this not only for prediction purposes, also in the EDA, in the exploratory data analysis. I think that you should, if you're doing a regression project, you should use regression tree to understand your variables. Now, let me show you how it works. So the idea here is like the most important variables to make the prediction are going to be on top of the tree. So here Rm, the variable Rm is really important because it's the first variable. This is the average number of rooms per house. Now, initially, there are 404 observations. This is samples value. And the value is just the y value. This is the median value or the average of the dependent variable. Okay, so the tree is suggesting that, okay, this is the most important variable, and this point 6.8 is really important for that value. So if the observations or a specific or one observation has a value of Rm smaller equal or less equal than 6.8, then we go to the true, so that's to the left, and if it's higher, you go to the right, to the false. So smaller houses than this, they will go to the left, and bigger houses are going to the right. So please notice that now the values in the houses that are here to the left, those that are below 6.8 Rm, the value is smaller, right? The average value. Initially, the average value was 22.77. But now for this value, for these houses, or for these areas, the median value is 19.59. Now, if the houses are bigger, then the average value is 35.82. So you see a huge means difference, right? That's why the algorithm is finding that this cut at this specific value is important, because the mean difference is huge, it's big, right? You can see it. So that's why the partition is at the 6.8 for that specific variable, because it's significant. Okay, now you can keep doing the analysis. So here you have the LSTAT, the poverty level in the area. So if it's below 14.4%, you go to the left. If it's higher, you go to the right. Please notice again that if the poverty level in the area is below this threshold, then below equal this threshold, then the value is 22.7. But if it's higher, then it's 14. So it makes sense, right? If you are in a better area, the median value is going to be higher than if the area has higher poverty levels. That's common sense. So this is how you can go, like to the bottom of the tree. So this is where you make predictions or where you understand your data. So for example, if you're like, how do you use this tree for prediction? So you have an observation where the number of rooms, the average number of rooms is below 6.8. Okay, you keep going from this side. The LSTAT is smaller than 14.4. You go to the left again, and the LSTAT is above 4.6. Then you go to the false side, this one. If that happens, then if you have a new observation with these variables within that range of values, then the prediction is that the median value is going to be 22.2 K, right? So that's how you use the tree for prediction purposes. So you just go throughout the tree until you go to the bottom level where you have the leaves, and the prediction is going to be the average value here. So pretty much it uses partitions and historical data to make prediction. So whatever is new, a new observation, the prediction is going to be the average of properties that are similar to that one, but according to the partitions of the tree. All right, so that's for regression. Now, this is an important question. How do you know that this is a regression problem? We know that this is a regression problem because the dependent variable, the outcome or the output of the model, is a numerical variable. We want to predict price, right? Price. So that's why this is a regression problem. We want to predict a numerical variable, price, using independent variables. Now in our next problem, and this will be our last problem in the video, this is a classification problem that we have used before, the breast cancer dataset from scikit-learn. The y variable here is whether the tumor is malignant or benign. So that's a categorical variable. That's why this is a classification problem and not a regression problem. Okay, so same thing, we create our tree. Here I will use it not for predictive purposes, I want to do it just more for exploration, for the exploratory data analysis. Okay, so remember that the outcome it's where the tumor is malignant or benign, and there are 10 independent variables. They measure the radius of the tumors, the perimeter, smoothness, and different metrics. Okay, so the most important variable here, according to the classification tree, is the worst radius. of the tumor. The Gini coefficient, this is a metric that is used in economics. It measures like the equality in a society, like how the the income is distributed in the society. So if it's close to one, from the economic perspective, that's good because you have like it's like everyone is equal to each other in terms of income. But if it's close to zero, that will be a problem because it means that there are like huge inequalities. That from the gender perspective, that's not desired. Now that's in the economics context. Here, when we are classifying, actually, it's important that we minimize the Gini. We want a small Gini close to zero because if we're doing that, we're classifying. That means that we will have more observations in one class than in another with using our tree. And you will see that in the once we start going, like down in the tree. Okay, so initially our gene is close to 0.5, and values there are in total like 569 observations in the data set. The zeros we have 212; those are the malignant tumors, and 357 that are benign. So 0 and 1. Okay, so if the worst radio is lower equal than 16.7, we go to the true, to the left. If it's higher, we go to the right. We are not doctors here, or I don't know, maybe there is one doctor in our class, but common sense will suggest that if the worst radius is smaller, so most likely I guess it's going to be a benign tumor, right? If it's greater than this value, if it's bigger the tumor, then it's more dangerous, so most likely it's going to be malignant, right? Again, this is just for the sake of the analysis. Please do not take my word as medical advice or anything like that. It's just common sense. Okay, so let's check that. So okay, let's check what happens with the tumors that have a worse radio less equal 16.7. So they will be here to the left. Please note how the distribution is changing. So now here, like the a high percentage of the tumors are located as ones. That means that most of the tumors that are with a worse radio that is small, or at least smaller than that value, will be benign. Now, of course, the opposite is going to happen in the other side of the tree. If the worst radio is big or bigger than 16.7, then please notice here now the distribution. Now here we have a higher number of tumors that are malignant, right? So we're classifying, and that's desired. That's what you want here. And the gene is decreasing, it's getting closer to zero. Initially it was 4.6, 4, I'm sorry, 0.46. Please notice that now it's 0.1, 0.15, and 0.10. So it's decreasing because we're classifying, and that's desired. That's desired. You can keep going, but for EDA purposes, uh, one way to use this classification tree is you just go to a leaf here, and you can identify, okay, where do I have like the biggest number of observations? So that will be in this leaf we have 332, and also in the last one we have 172. So like most of the observations are located in the tulips. And now we can kind of like analyze the profile of the tumors that are here. Please notice the values 4 and 328. That means that there are only 4 malignant tumors here, and there are 328 that are benign. So from the EDA perspective, it's really nice to see, okay, what are the characteristics of the benign tumors. So we go up in our tree and we see, okay, they are small, the worst radio is smaller than this value, 16.7. Then the worst concave points, they have to be less equal than 0.13. And finally, the perimeter error is less equal than 6.5. So if these three values for the variables are within the ranges that we have in the tree, then most likely, right, or yeah, there is a high chance that the tumor is going to be benign. So that's really important when you are analyzing your data, understanding, getting insights. And now we can do the same analysis for here. And please notice that in this case, most of the tumors are malignant, right? 171 malignant, and there is only one benign. And we need to check what are the values of the variable that will lead to this conclusion. Okay, so we go up. So in the worst radius, it's bigger than 16.7, that means a big tumor. And the worst texture, it's greater than 19.91. And the worst smoothness is greater than 0.08. Then these three variables suggest that most likely the tumor, this is according to this data. Please do not generalize. Again, this is just scientific data. It's for academic purposes. But you will see that it's very useful for the EDA because now we get an idea of what are the characteristics of, like this class, the malignant tumors, and also for the benign tumors. So trees are really, really useful for interpretability. Sometimes it's not just about like finding a good model with predictions with high accuracy. You also want a good model that can be easily understood by people, that everyone can be using, and that's really important. The interpretability. Okay, so I'm gonna finish the video. So here there are some conclusions about this lecture. So the tree-based visualization that are really effective when we have hierarchical data, as you were able to see in the examples that we covered, especially the tree maps and even the decision trees. So decision trees, they are really important, not just for predictive, we can also use them for in the EDA. And actually, I highly encourage you guys to do that, to take this regression and classification trees not just to the predictive stage. You can use them also during the EDA. That will make you look like stronger as a data scientist. Dendrograms are helpful when you want to explore observations, like which are closer to each other, so they can create a group or a cluster. So dendrograms are really useful for that. There are other variations of tree maps. So we just covered the tree maps which are with rectangles, but I highly encourage you to check the Sunburst, which is it's like a enhanced pie chart. But again, just give it a look. The more tools, the more alternatives you have to present your data, the better. So because at the end of the day, choosing the right visualization will depend of the context, the interpretation, what you want to show. So there is no okay, this is the best visualization. No, it will depend of what you have and what you want to, the ideas that you want to convey. All right, I'm gonna stop the recording for today. I'll see you in our next lecture.